Exam time. So I hope you appreciate these extra hours that we have. I know they're not being put to optimal use with COVID, this and that. Obviously there's consequences. But because of those extra hours, we're able to arrange things that this whole lecture can just be nothing but a review. And of course I'll do this before test 2 and test 3 as well as the final exam, which I will have a 2-hour review session for, which is kind of tough. Alright, I'm also releasing this early because why not? And I'll do the same on the other exams. And let's see, now the other thing that you're all asking for is what exactly is the format. I think I've mentioned it a few times. That's okay if you don't recall, that's fine. I'm going to review it as well, and it will be what I said before. Alright, so there's 3 sections to the exam. Number 1 is, now I'm trying to recall. Oh yeah, I'm trying to recall what's on the exam. I just wrote it, by the way. What's wrong? Okay, now this is it starts out with, there's like 4 of these, I think. It's like, here's a question, it's like a middling homework question, but then I work it, but I do it intentionally wrong, and you have to identify what's wrong. Now, I've already had people email me and say, well, then I have to work the question right. No, and here's how you know that. It doesn't say to do that. You simply identify what's wrong. Okay, so the reason I'm doing that is, as I've said a couple of times when I mentioned I was going to do this, because knowing what's right is great. Knowing how to do things is great. But a lot of how our society runs along is that it just runs along by itself, right? Now, if you want to be a doctor and a healthy 20-year-old comes in, there's really nothing for you to do. You're most valuable when you identify what's wrong. Also because, to be blunt, in terms of like the material of this class, you demonstrate, real in-depth knowledge by identifying problems. If you really don't know what's going on, you could never do that. Okay, now in terms of what types of questions, let's see. I gotta recall. I've got derivational questions where I will mess up the derivation. I may use the wrong identity. There is a cheat sheet with the right identities. You could look there and see that I used the wrong identity. I could use the wrong equation. There are numerical questions. So you bring a calculator. There are numerical questions. I have not done something so cheap as to plug in the numbers incorrectly. I didn't go there. I could have. That would be fair game. But I didn't do that. Instead, what I would do is mess up the constants. Okay, so mostly derivational, it's some calculations, and again, the calculations were messed up by using a number incorrectly in some fashion. Often there's more than one thing wrong. I only ask you to identify one. There's one of them where there are 5 separate mistakes. And again, just identify one of them. So that's about that. Then you've got questions. So there's like 4 parts, like A, B, C, D. Then you got questions. Oh my God, I forgot. I think there's about a total of 15. 12 or 15, I don't quite recall because I have subsections anyway, so I think that, let's say there's 15. So 2 to 12 are short answer. Now, these are mostly descriptive questions like what kind of mathematics is involved in quantum mechanics? Well, those are all eigenvalue equations. They're all second-order differential equations. Now, I've said that a zillion times. So when I ask descriptive questions, I know that I don't do those on homework, and that's just because there's a lot of math in the homework, which is what the point of the class is. But because of COVID, I have to bias the exam towards more short answer because you have to type this in. You have to type this in the Blackboard. I know that short answer is just easier to deal with. So I have a lot of short answer questions that I normally wouldn't. Now, notice that in my previous example, you could just type in, oh, we do eigenvalue equations, and a lot of there's a lot of differential equations. Now, the types of questions I ask are things I've said ad nauseum. And I know that I said eigenvalue, differential equation. I've brought those up over and over and over again, right? So there's not going to be any minutia. The one thing I said that one time at the very end of the third lecture, nothing like that will appear in a short answer. Okay, now, there are some derivational questions, and those are very similar to the homework, but they're short. They're like, here's an identity, solve it, and whatnot. Okay, then the last questions, and again, I'm not saying that there are actually 15 questions. I haven't quite, I've written a bunch of questions, but I'll shrink the test just because. Actually, I've written 20 questions, but anyway, these are derivation. Okay, one's easier and the other two are a little harder, but again, it will be almost identical, but not the exact same thing as what you've seen as identifiable derivational questions on homework. Here is a distribution function. What is the average cat, right? Solve the normalizer, do with an identity, multiply the distribution by cat, and then integrate or sum it, right? You do all these questions by looking at identities, and again, you have the cheat sheet with the proper identities. You should be able to do those in just a matter of like 4 or 5 minutes. It's just a matter of identifying identities, right? That's really all you ever had to do. Now, I believe I have scheduled, I think I give you about 15 minutes to do each one. I'm certain you can do it in less than 5. But you have about 15 minutes to do each one. So there's 3 of them. Easy one, 2 harder ones. All right. So that's the structure of the exam. Again, on Blackboard, I'm having you do what you did with Hemorrhage because you're used to that, and that's fair. You know, we have lots of problems. You know, I hate to start out with this, but we have had academic dishonesty problems like we have never seen before. Roughly a tripling of complaints, and so we're taking a lot of steps. We have to take a lot of steps to put a stop to that. So anyway, that's one of the reasons I have. There are a larger number. Normally, I wouldn't have this number of questions, but there's a lot of questions to just kind of keep you on your toes. That's one of the strategies we use. Okay, anyway, so that's enough about the actual thing. In terms of review, and as I promised, I had written this review after I finished the test. I just wrote the test. I wrote it over 3 days. It's been error checked. That just happened a few hours ago. Once that was done, I wrote the review notes. I only wrote these review notes after I had the test after the test was written, after the test was in hand, so I make sure that I'm going to cover the material on the exam. Now, I noticed that a lot of the times for the people who don't score high, you miss something I directly said during one of these review sessions, and I don't know why that's happening, other than maybe they didn't watch the review session. So if that's who you are, then you're not even listening to me, so I don't even know why I'm talking. But if that's what you're going to do, I don't know why you would think you're going to get a high score. But again, I'm talking to no one, so maybe let's just go ahead and talk about, let's see, what did we begin with? We talked about how averages, an average is not just 5 numbers added up divided by 5. Again, that's a kindergarten type. You know, now you know that the real math equation is a probability distribution, and let's make it of energy integrated as 1, so you multiply by the thing you want the average of, or if it's, that's for a continuous, that's when energy can have any value. If you're doing like, let's do number of photons, the Planck distribution, you ran into the same thing. And energy was hc over lambda times the number of photons, and then you had the probability distribution of the number of photons, energy of the photons. And in either case, right, so in this one, we do an integral, energy times the probability distribution, because energy can take any value, and so that's an integral. In the case of Maxwell-Boltzmann, the average energy is it's the same thing, it's just that because you either have 0, 1, 2, or 3 photons, you don't turn it to an integral. It stays a sum. That's okay. We find the identity, and there is an identity for that, and you write that down and you're done. What I find kind of interesting about, especially what became clear, I hope it became clear, in the Planck distribution part was how the average energy ended up really not being the average energy, it was actually the average number. I don't know if you noticed that. I did try to call attention to that fact by all those homework questions. Now, I know I flubbed one of them, but there are questions like this on the exam where I have some kind of formula for something, like, you know, the cost of a cat is like $1,000 times $1,000 times the number of cats. Then I tell you the average number of cats that like I have is 2, and therefore the average cost of a cat, at least in my household, which is about right, come to think of it, I really do, anyway, is about $2,000. So I have questions like this. All right, anyway, so I'm kind of diverging here. Okay, so when it came to, so these are the proper averages. Again, I know we did this with Maxwell-Boltzmann, but when we did Planck, you also saw summations. The Maxwell-Boltzmann distribution itself is, of course, this thing here. And so this is for any particular energy. The normalizer is always on bottom. Remember that what's interesting about Maxwell-Boltzmann is that it has a normalizer to begin with. Remember, on quantum mechanics, we often solve wave functions. That's like the top part, but they don't come with normalization constants. You have to figure that out. You have to figure that out on your own. That's one of the big differences between quantum and the Maxwell-Boltzmann deal, is that the probability distributions from Maxwell-Boltzmann equation has a normalization that comes with it. Recall the strategy for solving this. You always have to go for the normalization first. That's got to be turned into something. By something, I mean a bunch of constants. M over kBt, blah, blah, blah. 1 minus e to the hc over lambda, blah, blah, blah. It can't be a sum or an integral. It has to turn into something, right? So in the case of Maxwell-Boltzmann, we ended up with, now we had to work in 3 dimensions, which was a detail that is only applicable to the Maxwell-Boltzmann. And you have to have some knowledge about when are you working in 1 dimension or 3 if it's not apparent from the problem. Of course, I make sure that you know that. Now, that's the Vx. There's a Y. I'm just going to do this if you don't mind. And a Z. So this one was a hard one, right? You may recall appropriate limits. Of course, when you have to do averages, I make sure that you know the appropriate limits. And of course, the business end stayed the same. And one of the big pictures here is that the way that we turn this energy into a velocity distribution is merely by inserting 1/2 mv squared in for energy. Remember I said this in one of the videos early on? It's just fascinating, right? This is a distribution of energy. We can figure out the average energy and the most probable energy and all that stuff. But by simply inserting 1/2 mv squared and do the normalizer again, I said that a zillion times, then it's now a function of velocity. But it's still energy, because it's still 1/2 mv squared, that's still energy, but I don't see an E in it, I see a V. And now that it has V in it, I can do all the stuff I need to with V. So it's something different, yet the same at the same time. And it's kind of hard to get your head around it, but it is what it is. So that's the neat thing. Just substitute 1/2 mv squared for energy. Now we could also substitute momentum and whatnot. There's all kinds of things we were able to do with that. And yeah, there really isn't much else to say. Now recall that once in the one of the hard derivation questions is I give you distribution, and it's going to be like kitties in a house or something, or it's COVID patients, by the way. And you solve the normal, you figure out what the normalization constant is, and then you go from there. And in our case, let's see, what does this turn into? This turns into 4 pi. So we have a Jacobian. I'll talk about Jacobians in a second. The normalizer does this part. m over 2 pi kBt to the 3 halves e to the minus mv squared over 2 kBt. Okay. Okay, so that was the distribution function. You can plot it and do all those kinds of things. I don't think I had you do anything with graphs. I don't have you do anything with graphs on this present homework. And let's see, we were able to do things like calculate the average velocity. So that's the Maxwell-Boltzmann distribution. Then we're able to calculate the average velocity. And remember that always take this thing. Remember, this is a big theme in all of this. Take the distribution and multiply it by the thing you want the average of. That's why v times 4 pi v squared is 4 pi v cubed, right? So now I'm calculating the average. And the way you know that, if you mess this up, if you do this calculation, if you integrate this, you're going to get the number 1. That's how you know you messed up. If you did it right, what you do is you write it out correctly with a v cubed and not a v squared. Then you find the identity, right? Take out the constants, find the identity. You do need to know how to use identities correctly. We have done that over and over again in all your various homeworks. And what you get is 8, and don't worry about simplification. I don't have you do that, but in this case, I'm just simplifying the result. I'm not showing you the identity, but anyway, so you just simplify the result. I'm simplifying the result, and there you go. So obviously there's opportunities there for what's wrong questions and whatnot. And I do have you do 3 or 4 of these. I give you a distribution function, what's the average? So that's just specific to that one. Don't forget that we also have most probable is very different than average. Most probable comes about by taking the derivative of the Maxwell-Boltzmann velocity with respect to velocity. Now, as soon as you set that to 0, then I have to stipulate that that is the most probable velocity, because when you set it equal to something, you're saying that it's not just any velocity. You know, the derivative of the Maxwell-Boltzmann with respect to velocity is whatever it is, but when I set that equal to 0, then I'm saying that it's one specific velocity. So, and this guy comes up on the exam as well. Let's see, is there, and one other thing. Let's see, I got just one other thing. I also have you relate variables to each other. You had one homework question, and so I have one on the test. Let me give you an example. So let's say that the most probable energy is kBt over 2, and the most probable velocity is 2 kBt over m, and of course that's square root. Otherwise the units don't work. And now I ask, how do you relate the two? Okay, I'm going to start here. I'm going to say most probable squared is 2 kBt over m. So all I have to do is multiply that by m, and that's gone. I'm almost there. It looks like I need to divide this by 4. When I do that, 2 over 4 is 1/2. And now I've got E most probable. Okay, so you just saw me do that, and it's not particularly hard. I'm just testing some of your basic algebra skills, to be blunt, but it is kind of interesting. You know, you do see some like weird things, and I don't understand this, by the way, but why is it not 1/2 m V most probable squared is E most probable? See that? 1/2 mv squared is energy, yet we have 1/4 mv squared is energy, as long as we're talking most probable. I don't get why that is. I need to try to look that up, but these are the reasons that we do these kinds of things, because we occasionally run into some like really, really odd relationships. I don't know why that is, but I think it's kind of neat that it is what it is. Let's see, what else have I got here? Yeah, I think Jacobians. Oh my God, Jacobians. Jacobians are a big part. Two Jacobian questions. Now, I can't say that necessarily that you're going to get those. Let's see. Okay, now the Jacobian equation is on the cheat sheet, and what I say is that, remember, Jacobians are for when we are switching variables in an integral expression. Okay. Now that sounds like a very specific thing. I have an integral expression and I'm switching variables. When am I going to do that? Well, you did it like a freaking zillion times in this class so far, so yeah, it's a thing. It's a thing because there's so many different kinds of like velocities. We can have velocity, momentum, we actually switch to energy. There's so many things you can turn one thing into another, like energy into velocity by 1/2 mv squared. That's great. I mean, there's really a lot of things we can do with that, but you have to, but everything's an integral, so you've got to switch the variable of integration. Now, recall that there's two parts to this. This is on the test. There's two parts to this. What we're going to do is we're going to switch out x for g of y. Now, y is our new variable. Identify that. Y is the new thing being integrated. Like we started out with Boltzmann of energy, and we end up with a Maxwell-Boltzmann of velocity. So x is z and y is velocity. Now, there's actually a function of velocity that's energy, which we know to be 1/2 mv squared. So that's the g function. All right. It's just important to keep it straight. It's just bookkeeping. Identify what's what, keep track of it. Okay, anyway. So the trick is, to these integral expressions, one of the ways to also keep track of how to do this right is do this in your head. Nothing changes. This is equal to that. It has to be the same thing. Okay, so what do I put in terms of the big function? X, if the big function is a function of x, it still needs to be a function of x. G of y is still x after all. This is f of x. This is still f of x. E to the energy, e to the 1/2 mv squared. That's still energy, right? Now, if you get this far, you get half credit, which recall in a class with my scoring system, that's an F. Okay, it's better than 0 points, but you want more than 50% credit. The reason I'm calling this 50% credit is that this is half the question. Jacobians, right? Now, I spent a tremendous amount of time on Jacobians. Right, so there you go. Recall that, okay, we've identified g of y, like in the example of x is energy, y is velocity, and again, keep this, if this is the problem, keep track of it, keep track of all this, write all this out. For what function of velocity is equal to energy, well that's easy, that's 1/2 mv squared. Okay, so if you have a problem like this, write this down, and then when it comes to the Jacobian, it ends up being quite easy. G of y is 1/2 mv squared. We've already identified y as v, right? And then it's just mv. Right. So there you go. Blah, blah, blah. Now recall that, again, this is still f of x, just like I said before. Okay, this is the change in x with respect to y, times the change in y. And again, my point here is you see how the expression never actually changes. This is still that, right? And clever, right? Again, I'm harking on this because if you can retain that this thing fundamentally never actually changes, and you remember that you need to do a Jacobian, you should get through those answers quite readily. It should not be too hard. Okay, next bit, black body. Okay, give me 1 second to wipe out the board, and then we'll do black body. All right, we're back. You know what? Sorry. Let me just review this whole Maxwell-Boltzmann bit one last time, because when it comes to one of the derivational questions, and as you've had on your homework, I don't know that you really need to know how fast a gas is moving. That sounds like something that maybe an airline pilot might need to know, but even then I don't think so. So that's why for your class, I've done a lot of how many average COVID patients are there, and yes, I talk about the cats, but I'm going to do that anyway. For your exam, I have a problem like this, and so, and I've already said that, but let me just point out that when you see this, remember the approach is to identify, you figure out the normalization first. So you identify, yeah, no wonder I got confused. You identify the identity from the cheat sheet, right? Now notice that this can go one of two ways. If I have cats, you're going to be looking for a sum because cats are either 1, 2, or 0, 1, 2, or 3 cats. If it was like water volume, then you want to turn that into an integral. You'll know you got it right when you find the right identity. Okay, so then what you get, once you have that information, you would then figure out, in the case of number of cats, which would be discrete, that means 0, 1, 2, 3, you would then have cats, it's been normalized, I'm not sure what that normalization is. You would then have this expression, you find the proper identity, and you basically just write it down. Write down the identity with the parts filled out, and there you go. So anyway, last bit about Maxwell-Boltzmann is there. Again, I just wanted to bring it up because I don't really think there's much value in knowing how fast a gas molecule goes. It's just that it's traditionally taught in this class, but it's more important that you understand a bit about probability in general. A little over half the exam is on Maxwell-Boltzmann, but a good bit of blackbody stuff appears. And so the first thing to note about blackbody was I defined the light bulb as, I said basically a light bulb is like a cube. All right, here we go. The light bulb is L big, and it's about 2 centimeters. I tend to use 2 centimeters in my calculations because that's about right. Okay, and as is very familiar to you after this week and a half of quantum, recall that I said that the photons have to fit inside the box, which perfectly makes sense. You probably just never thought about it because why would you have? Anyway, so the light waves have to fit in the box, so no duh. We also, so you're able to figure out like what the functions are, and then we have like our own Schrödinger equation. We had Maxwell's equation, and you may recall that was like this. I'll just do the one-dimensional form, and I'll write this in a very mathematical way. Right, mathematicians would be confronted with an equation that looks like that. What we figure out is that what you're supposed to apply is the equation for the electric field, which is unfortunately E. Like, I know it's like energy for quantum, but for Maxwell-Boltzmann, it's the electric field. And we can, if you're given the formula, so I can look at this and I can see that the proper formula is sine. There's like a mode number later that would be called a quantum number when we did quantum. And then we had, of course, a specific one for, I remember, 2 pi. There we go. I'm doing that off the top of my head. Anyway, so you can plug this into here, and then you're able to relate the number of nodes to the wavelength that fit inside the box. So that's just that was just an early step of of our approach to this. And then we did in 3 dimensions. I'm just trying to do this a little bit easier. Again, remember that our little n sub x here was the number of nodes. The higher the mode number, the more nodes there are, the shorter the wavelength. So this has 1 node. And later, like I say, those end up being quantum numbers when we started getting to quantum mechanics. And you're going to see a lot more of those after this exam. Okay, so what about it? We then were able to figure out what wavelengths fit inside the light bulb. And the number of wavelengths, let's see, that went only up. And there's a cutoff, right? Because you can't have a wavelength bigger than the light bulb. So that's one of the things that we found. But this isn't what the intensity of a light bulb looks like, which is like that. So what went wrong? What went wrong was we had to calculate the average energy of a photon, which we then did Boltzmann, and I've already talked about this already specifically, so I won't mention about that. But yeah, I mean, that's really all it comes down to is just noting that, of course, the energy of a, and this is now energy, by the way. I know there's two E's, right? I tried to put a little hat for electric fields. Sorry about that, there's nothing I can do about that, it's the English language for you. Just remember that what I got kind of, what I thought was interesting was that the energy of a photon is hc over lambda, but the trick is to note that you can have more than one photon. So the energy that you derive ends up being related to, you know, hc over lambda are just constants. What you're really calculating is the average number of photons. And again, you saw that idea repeated in several questions, and again, it makes it to the exam. So the reason that the Boltzmann, sorry, I didn't really draw this right, that bothers me. So we know why the Boltzmann distribution initially rises, because that's proportional, it's actually proportional to, I think it's 1 over the wavelength. I think it's ultimately, no, it's ultimately to the third power, right? That's because there's a rise because more photons fit inside the box. So that part is dominant, the first part, but then what happens is you have an E, this part dies off because it's proportional to E to the minus energy over KT. Okay, so what ends up happening is the reason it doesn't rise forever, so this is the intensity of light, sorry I'm not doing such a great job here, rises because there's more light fits in the box, but it dies off because as you get to shorter wavelength, the average energy ends up having a Boltzmann E to the minus energy over KT. Now, the photon's energy, when you get to like UV and X-ray, those are really high energy photons. That's why they would destroy you if you ever got exposed to lots of X-rays and UV, it kills you. And so that big energy over KT ends up being E to a big negative number, which is 0. So that's why it dies off. As you get to shorter wavelengths, the energy of the photon itself gets bigger, but KT is still KT. Remember, KT is a measure of the thermal energy things have by virtue of being hot. So our light bulbs are around 5,000 degrees. You can't get them much hotter because they melt. That's why you make light bulbs out of tungsten. So T is around 5,000. You're not going to really do better than that. And so if your photon energy gets higher and higher, E to the minus energy over KT ends up becoming a smaller and smaller number, and that's why it dies off. Okay, so that's why you have a rise and fall. And I tried to emphasize that when I mentioned the Rayleigh-Jeans law in your last homework, because when they applied the equipartition function to the average energy, they found that the intensity of a light bulb would only go up and up and up. They never thought about the fact that a high energy photon out of a light bulb is improbable. That just didn't enter their head. So obviously the results were like crazy wrong. Let's see. All right, so I do have a decent number of Planck distribution questions on the exam. They are mostly, there's a lot of this, there's one like this, so there you go. And then I have other descriptive questions. Remember I know it's a little crude, but I wrote a little 9-page handout on how to do this. So that should, all your questions are in there, all your answers are in there. Last bit is quantum. We've spent a week in a lecture. So I'm trying to put, this is being put up Monday. Today's Monday. The lecture you had today has 2 questions on the exam. Watch Monday's lecture. Watch the last lecture on quantum. 2 questions from that lecture made it to the exam. That's why I always have the review right before the exam. I don't do them on Friday because I know that a lecture would come up and I know I'm going to put that on the exam. All right, so anyway, so what about quantum? Let me get a new board here. Okay, Now, I didn't put this on the exam, but recall that I didn't put this part on the exam. Einstein's relativity. I did not, let me be very clear, let me make sure I'm speaking clearly. I did not put any relativity, this thing, mass increases with velocity. I did not put them on the exam. I just didn't. Now, I can't ask about everything. There's not that many questions, right? I don't have room for everything. Anyway, I just hope that it's kind of neat to know about that kind of stuff, because it's like those are the geniuses of our society, the Stephen Hawkings, and now you know something about it too. The reason I bring it up at all is that from here, and now I may ask you about stuff like this, by the way, is that Einstein figured out that light had momentum. And remember, that's remarkable that light has momentum because it doesn't have mass. And that was because our fundamental understanding of what momentum is not correct. You can have momentum but not have mass, and that was why the guy got the Nobel Prize. Okay, so again, this is all relativity. But de Broglie, the derivation's a little bit more complicated than this, but he basically rearranges it. He says that things that have mass, momentum is still mv, and you have to have mass to have mv. So particles still have momentum, so therefore they have a wavelength. All right, so that is where quantum mechanics begins. And recall then that Schrodinger comes along and does this deal. He uses an eigenvalue equation, right? And a couple of things to note about this is the equation that describes musical instruments. If you want to know, like a violin string, a piano string, it vibrates. Think about it, it's just like a particle in a box. It's like a photon in a light bulb. These are all the same thing. Now Schrodinger knew that, so oddly enough, he uses an eigenvalue equation to solve the structure of things. Again, one of those things could be a piano wire. It's all the same. So the guy knew that. I thought that was always kind of cool. Except that instead of describing a piano wire, it's p squared over 2m. Now, potential energy, but not on this exam, is equal to energy times the wave function. And later he would figure out that the momentum operator squared is minus h bar squared over 2m. Double derivative, momentum squared operator is minus h bar squared double derivative with respect to position. P squared over 2m is minus h bar squared over 2m double derivative. Okay, apply to a wave function and you get energy times the wave function. Now a side note, recall that I started you out with this, but I wanted you to know the real truth, which is that quantum mechanics has all kinds of operators. So this is a specific form of what I am putting here. And it's a detail, but it kind of is important. This is, of course, these are both let me write that. Eigenvalue. These are both eigenvalue equations. When I put it this way, I want to point out that we have all kinds of operators. We have momentum, we have position, we have energy, which is special. It's called the Hamiltonian. We had others like flux. We're going to have others in the next section on rotation. Anyway, there's a bunch of these. There's like 20 or 30 that I know off the top of my head, and you've seen a couple. And the wave function the eigenfunction is whatever works with that. You've always got to see this happen. You've got to apply the operator on the function and get a number times the function. If you don't see that, it's a fail, right? Anyway, so I brought this up later, and of course the Hamiltonian is special, so it gets its own symbol for its eigenfunction, which we call a wave function. And that's what Schrodinger developed. Now, if we're going to remove potential, we've got our free wave, right? So without potential, we're doing a free wave. Now remember, the free wave problem is a great way to start learning what a wave function is. And in this case, the wave function was very simple. It was just cosine kx, where k is the wave vector. And I actually introduced that when we started talking about light. and it's 2 pi over the de Broglie wavelength. Right. So that ends up being really, really important because we're able then, with this, we can plug that into the eigenvalue equation, and we find that the energy is h bar squared k squared over 2m. So basically, this wave vector tells you the energy. Now, we are also able to ask other questions like the momentum on the wave function, and in this case, sorry, let me, we have to start talking about expectation values. Let me just point out that the momentum happens to be h bar k. So wave vectors are basically momentum, and of course momentum squareds are energy. So all of this is consistent, right? So again, let me point that out. This was your first foray into what a wave function is, cosine, right? K was just 2 pi over lambda. That makes sense because when x goes from 0 to lambda, cosine goes from 0 to 2 pi. We see that K shows up in the energy, and we know it's related to momentum. All right. Now, the next thing that we ran into that was really a bit of a biz knocker, it was rather unfortunate, was that we then had to do expectation values because, and we did that for momentum, because this will fail a decent number of times, right? So recall that while cosine is okay with the Hamiltonian, cosine was not okay with other operators, and specifically the momentum. And that's one of the weirdest things about quantum mechanics. And I can't really do better than that than just to tell you that's how it is. Cosine may be the right wave function for the Hamiltonian, but it's not right for the momentum. It just isn't. There you go, we're done. Now, the only other thing to remember about that is when you've run into that situation, when the eigenvalue equation has failed, you then go to expectation values, right? So that's what you got to remember. I don't think that that's that bloody awful, right? And that ends up being a complex conjugate of a wave function, operator, wave function, and we're still just in one dimension, so dx. And you do that, you look at an identity, and you get an answer, right? Now, cosine, recall that we are able to figure out that for free wave, cosine and sine, the average momentum is 0. And that was because the free wave, for the free wave functions cosine and sine, what's happening is these are composed of e to the ikx and e to the minus ikx, right? So plus or minus. So free wave sines and cosines are composed of a right wave, e to the ikx, and a left wave, e to the minus ikx. So what that allows them to do is to have, for sine and cosine, the average momentum ends up being 0, just like I just said. It ends up being 0, yet it still has, it still is moving with h bar squared, because it has h bar squared k squared over 2m energy. So the conundrum of it has kinetic energy, but an average momentum of 0, those sound like they don't work. It does because the answer is you don't know whether it's moving left or right. And whatever the momentum is to the right would be averaged out by the momentum to the left, right? That's perfectly sensible. And again, it's because sines and cosines are right waves and left waves. And we know that e to the ikx and e to the minus ikx, those are okay with the momentum operator. So e to the ikx and e to the minus ikx are really weird oddballs. And this is what makes quantum mechanics. Some things that are okay with this, like cosine sine, e to the ikx and e to the minus ikx, are okay or not okay with other operators like momentum. The expectation value thing will always work. So note that. Now recall that you have to do things like normalize. I do have a normalization question. The example from Monday's lecture, the last lecture, there's an example there. That's very similar to the one on the exam, by the way. So I'm giving that one away. Let's see, and I don't know what else I really want to mention. I think I'm kind of out of time. Yeah, I'll just mention one thing, since I do have, I was kind of surprised how many things came up on that last lecture on the exam. Of course, quantum builds up on itself, doesn't it? Let me just cover one last thing, which is that I do have some uncertainty principle questions on there. And the last thing we talked about on Monday's lecture was that if you were to make a measurement in position and then measure momentum second, and of course we're doing that on the wave function. If, however, you had measured momentum first and then position, you don't get the same thing. They are not equal. I know I didn't write that very well. Okay. So momentum, so if you measure position and then momentum, it's not the same as measuring momentum and then position. Those would not be the same. So if you subtract the two, you do not get 0. Okay, and that's related to the uncertainty principle. That says that it's arbitrary if you measure speed or position first or second. What does it matter which one you measure first or second? Neither is more special than the other. So I see no value in why I would do position first and momentum second, or momentum first and position second. I mean, it just is arbitrary. But the fact that you don't get the same thing means that you can never really know both. You can never know either with certainty. It also means that when you make the measurement, you have to be changing it. Now, so the reason that when you measure position first and momentum second is that the measurement of position has changed the wave function, and that's why the momentum returns a different value. Let me restate that over here. When you measure the momentum of the wave function, you change the wave function, and that's why you won't get the same position. And the difference of the two then is not 0. So anyway, and this is where we're going to launch into Monday after the exam. Other than that, I've got a bunch of office hours. I'm just looking through my notes. I did spend quite a bit of time on, just trying to recall. No, I think we're done. I did spend quite a bit of time on things like this, on your homeworks, like the math questions. Those don't make it to the exam. And that's not because, I'm not trying to screw you over. I just can only ask so many questions, right? And so I do need you to know this because we're spending a huge amount of time on this, right? So this is how the absolute value of an e to the I function works. It ends up being e to the 0, ends up being 1. So I know that I had to do a bunch of mathematical this and that, complex numbers, differential equations. They did not make it to the exam. So, but I don't want you to think you're wasting your time. As I said many times, your math skills are really important. That is what's going to make you a valuable employee. It makes you think better. You will prove that over time, but you need to have a foundation to do so, right? We are going to be using more and more of this as the class. The class will get harder as we move along, so you do need to know this. Again, it just didn't make it to this first exam, but on the second one, I guarantee you are going to be dealing with this because we do get into more complex things that have a lot more e to the I, k, x's in them. All right. Now, I think I've probably hit time, and I can tell you that the number of questions that I directly answered in this video is substantial. You'll believe me when you see the exam. And so not much else to say. If you don't believe me, then you're not going to do well. If you don't do well on this exam, it's okay, because you could, now, and I'm not joking you can do the math yourself. If you get a 0 in this exam, you can still mathematically get a B. So if you're freaking out about a couple of points during the exam, think about that. You could get 0 on this exam and get a B. Now, I don't think any of you are going to get 0s, okay? So that means that you're doing fine. But I do have to, put a disclaimer here. You can't do that twice, all right? You cannot recover from 2 zeros on exams. So remember, when you're taking this, the exam the goal is not to get a 0 now or in the future. That's not exactly the highest bar to hit, is it? Okay, so I'm done. Come by office hours, send me some emails if you have questions, and I will actually probably see many of you for the first time on Friday.